The RedHat Shield will be back in the Tindie Store within the next few days, so it's time to talk some more about the configuration and some details of the inner workings. Welcome to the IoTT channel, I am Hans Tanner. After installing the RedHat Shield on top of your Arduino stack as described in video number 99, you simply connect power and the system starts up. I only briefly touched on the power options in video number 99, so let me explain that a little bit more detailed. Following the instructions on the DCCX webpage, it is recommended to use two separate power supplies for the Arduino board and the power shield, and to cut the V-in trace on the power shield board. The reason is that the power pins of the Arduino and the power shield are connected via V-in, and that the two boards should be supplied with different voltages. The Arduino board works best if the supply voltage is around 8 volts. The track voltage, on the other hand, should be around 12 volts for N, 15 volts for HO and 18 volts for G-scale. If this voltage is applied to the Arduino board, the voltage regulator tends to overheat or burn. So the common solution is to use two separate power supplies, which is cumbersome and adds to the cable mess. The RedHat Shield eliminates this problem, as it has an onboard DC-DC converter that generates the 5 volt voltage for the Arduino board, so that the onboard voltage regulator is bypassed. As a result, the entire stack can be supplied with a single power supply, providing the track voltage. It can be supplied to any of the power inputs, as they are all connected through the V-in pin. However, if the power consumption of the model railroad is more than, say, 1 amp, it is recommended to connect the power supply directly to the power shield to eliminate high currents through the V-in pin. Okay, now the power is connected, the DCCX board and the stick power up. After about 5 seconds, the LED between the Loconet T sockets turns on, indicating that the throttles are powered. The blue LED next to the Loconet B socket may or may not turn on, depending on the settings for the initial power status. If the stick is powered up for the first time, it shows the Wi-Fi setup screen. Follow the example shown in video number 42 to connect the IoTT stick to your Wi-Fi or to configure it as access point. At this point, it is also a good idea to verify that your IoTT stick is running the latest version of the software, which currently is 1.5.14. As always, you can get the latest version from my GitHub page. Once the stick is connected, you can use a PC browser or your smartphone to display the node configuration page as explained in video number 99. In that video, I also mentioned the communication server options, but I did not really explain when to activate them. Here we go. Check MQTT Broker Gateway if you plan on using an MQTT broker to communicate with other Loconet devices using MQTT. You can run your private MQTT broker on a PC or a Raspberry Pi, or you can even connect to a public broker somewhere in the cloud. So if you want to move a train on your layout from 4,500 miles away, as I demonstrated in a short video a few weeks ago, that's the way to do it. Check the Loconet LB server checkbox to tell the stick to run a Loconet over TCP server. This is a protocol that is supported by several train control packages. So far, I tested it with JMRI and WinDigipet, and others probably will work as well. On the RedHat side, all you need to do is activating the checkbox. In the LNTCP server tab, you then can specify the port number you want to use. By default, it is set to 1234, and normally there is no reason to change that. On the software side, you need to tell the program to use Loconet over TCP to connect to the layout. In JMRI, you select Digitrax and Loconet over TCP and then enter the IP address and port number of the RedHat Shield. For WinDigipad, you choose Local Buffer as digital system and activate the LAN option to enter the IP address of the RedHat Shield and the port settings. Once set up, you can use your software package in the same way as you would use a USB connection, just via Wi-Fi instead of the USB cable. When using a standard Arduino board, the USB port itself can no longer be used, as the RedHat Shield uses the same serial port and protocol to communicate with DCC-X. If you are using a Mega board, you can redirect the RedHat Shield communication to one of the additional serial ports by running two wires from the RedHat Shield to the port pins and setting the jumpers as described in video number 99. Check the yThrottle server checkbox if you want to use a yThrottle app to operate your layout. When activated, you will see the server advertised in the app as soon as it is started. You then just click the server entry and the connection is established. On the yThrottle server screen, you can set the port number to be used, define how the power button in the app should be handled, and specify the DCC addresses of turnouts you would like to see in the permanent turnout list of yThrottle. The main part of the RedHat Shield configuration is done in the RedHat tab, which has 3 subpages for general options, inputs, and turnouts. The options page combines the typical op switch settings of a Loconet command station with the additional settings that come with the DCC-X software. Let's have a look at the individual options. Purging is the process of automatically releasing locomotives from the refresh buffer if they are no longer assigned to a throttle. Click the checkbox to enable the feature and then select the purge time and what speed the locomotive should be set to when purged. The track power up status lets you specify the track status when RedHat Shield powers up. Like on most Loconet systems, it can be set to on, off, idle, or restore previous status. Main signal on proc track makes use of a very neat feature of the DCC-X software. If activated, the programming track output carries the same signal like the main track, and programming commands are only sent if you enter programming mode. You can therefore connect an isolated track section directly to that output, and it will be usable as normal track, so you can drive a locomotive on the programming track without manually removing it from the layout. Allow no slot refresh is currently only a placeholder for a future functionality to extend the number of available refresh slots, meaning how many locomotives can be active on the track at the same time. The RedHat Shield at this time supports the 120 standard slots defined in Loconet, and the plan is to support the extended slots in the future as well, which will bring the total number of slots to about 400. DCC-X, on the other hand, when installed in the standard configuration on an Arduino Uno board, only supports 20 slots. This number is limited by the available memory on the Arduino and can be increased to about 60 if you recompile the DCC-X software. The no slot feature will provide a workaround for that limitation so that all 120 or in the future 400 locomotives possible in Loconet can be used even with the Arduino Uno setup. More on that in a future video, and if you don't want to miss it, make sure you subscribe to the IoTT channel and hit the bell icon to stay in the loop. Disable standard switch commands, also known as the push pipet, lets the command station ignore switch commands issued from handheld throttles. You can use this in a multi-operator session to prevent train conductors from setting turnout positions and signal aspects. Disable power on interrogation prevents the command station from sending out a sequence of switch commands after power up, which causes connected input modules like block detectors to report their current status. The fast clock settings line lets you conveniently set the fast clock time of the system and the desired clock rate. Note that any changes of the fast clock settings are immediately communicated to the command station and do not require clicking the Save and Restart button. The Reset Loco Slots button allows you to reset all locomotive slots in case something in the slot system goes really wrong. It is comparable to a system reset on a typical Loconet command station and should normally not be used. The second part, Loconet Options, lets you configure how events that origin from the DCC software are communicated to Loconet. Check Switch Echo to allow turnout position messages from DCC to go to Loconet. Check Input Echo to broadcast DCC input information, for example from unused pins, to Loconet. Click Loco Echo to do the same for locomotive information, for example if you change the speed of a locomotive on a local throttle. Right now this is a placeholder and the functionality will be available in a future version. Click Power Status Echo to send information about power status change to Loconet, for example if you click the power button on the side of the IoTT stick. Disable Switch State Report prevents the RedHat from answering to switch status request messages from Loconet. This might be a useful option if you have turnout modules that send their status information independently, which would lead to duplicate or even worse, contradicting messages. The DCC Generator section has a drop-down to select the track signal format DCC is sending out. Unfortunately, DCC is somewhat limited in this area as it cannot have address-specific data formats. The only possibilities are sending everything in 128 speed step format, which is the default and highly recommended, or sending everything in 28 speed step format. The 28 speed step format might be your option if you are using older decoders that do not support the 128 speed step format. Luckily, they are almost extinct by now. The programming track options provide fields for all the DCC configuration options for the behavior of the programming track. Please see the DCC web page for information when it might be useful to change to something else than the default values. In any case, if you get lost, you can click the Set Default Values button to restore the settings. The second page of the RedHat++ tab is used to configure additional inputs that are available on the Arduino board. Even when using a standard setup with an Arduino Uno and a power shield, there are a few digital input pins left that can be used to connect block detectors, buttons or other input devices. Even more so when using an Arduino Mega board or a HAL-based I/O module. And of course, it would be nice to make the information from those inputs available to Loconet, and that is what you can configure in this page. The DCC software offers the possibility to permanently store these settings in the EEPROM of the Arduino board. If you want to make use of this feature, check the checkbox below the table. However, it is optional because all information is also stored on the IoTT stick and downloaded to the Arduino at startup. When the configuration page is loaded, the RedHat++ Shield interrogates the Arduino board and displays all input settings that currently are configured. It also lists all settings that only might be configured on the IoTT stick but not yet on the Arduino. If an input is correctly configured on both sides, the DCC++ field shows OK, indicating the information is complete and without contradicting elements. If an input is only configured on the RedHat++ Shield, the field shows Not Set. This is also the case if you create a new input definition. And in case you have some pins configured on the Arduino, but not on the RedHat++ Shield, new entry lines will be created automatically, showing the Arduino pin settings, and the Loconet address field remains empty as it is not defined yet. So the table really is a hybrid display of what you have configured on the Arduino and what is configured on the IoTT stick. So let's have a look at the individual fields. The ID field shows the ID number used on the Arduino. Note that this number must be unique and the configuration table will not let you use the same number twice. If you create a new input, the table will automatically assign the next available ID number, so you don't have to worry too much about it. The pin number field has the pin number as used on the Arduino. For a Uno or Mega, this is the GPIO number on the board. If you are using a Hall component, there are defined pin number ranges depending on the number of the board. Check the DCCX web page for details. The logic field lets you specify whether the pin is active high or active low. This depends on the hardware you will connect to it. Up to here, all information is stored on the Arduino if the EEPROM checkbox is activated. The remaining fields have information that is only stored on the IoTT stick. The first is the message type. You can use an Arduino input to report either as block detector, turnout position, or button down up event, depending on what you are going to use the input for. And the last field is the Loconet address the information is translated to. This can be an input address, turnout address, or button number, depending on the settings in the previous field. When you click Save and Restart, the information is stored on the Arduino and on the IoTT stick, and after the restart, all DCC++ fields should show OK, indicating that the Arduino is configured according to the table settings. The last page for turnout configuration works in very similar ways, but here you configure the pins you want to use as outputs. The Store to EEPROM field works the same way as on the input page. In fact, it is the same option and it is not possible to only store either the inputs or the turnouts in the EEPROM. If you check the box, both types will be stored in EEPROM and the checkbox is updated on both pages. There are some more options though, as output pins can have different functionality, so let's have a look at the various fields. The ID field is the same as for the input and requires a unique number. Note that unique means it can also not be a duplicate entry from the input page. DCCX is a little bit more generous with ID settings as it maintains separate number ranges for each pin category. I found that this could lead to some confusions, so I decided to make it one single range of unique numbers for all categories. The DCC++ field works the same way as on the input page. It shows not set if the information on the Arduino and the IoTT stick is either incomplete or contradicting, and OK if the definition on both devices is identical and complete. If the current configuration of the Arduino has pins that are not defined in the RedHat Shield configuration, they will be added automatically when the web page is loaded, so that the Loconet related information can be added. The same is true in the other direction if a pin is defined in the RedHat Shield but not configured in the Arduino. It will be added to the Arduino list as soon as you click on Save and Restart, either just in the current configuration or stored in the EEPROM depending on the settings. So let's have a look at the various input fields. Turnout address is the address used on the Loconet side to talk to this particular output. Note that there is an offset of 1, so an address of 0 in this screen relates to turnout 1 in the Loconet world. The turnout type drop-down lets you specify the pin category as provided by DCCX. Now, this is a little complicated and maybe you have a look into the DCCX documentation. The easiest option to understand is DCC. What it means is the turnout does not use a pin, but instead the DCCX software sends a turnout command to the track so it can be interpreted by a switch decoder. Now, if you only want to control DCC turnouts from Loconet, there is not even a need to define them in this list. RedHat Shield will automatically send a turnout command to the track if it receives one from Loconet. The only reason to define a DCC turnout is to make it addressable from inside DCCX, for example when using X-Rail scripts. For that purpose, each DCC turnout needs to be defined and given a DCCX ID number, as this is the number used inside DCCX to operate it. The option you will most likely use for pins is VPin. This allows to operate a pin on the Arduino or HAL devices as a digital output that changes the output voltage based on the turnout position. Set the turnout to thrown, the output goes to 5 volt. Set it to close and the output goes to 0, or vice versa if you reverse the logic. This output can then be used to operate a turnout, but it must be changed to the voltage level and waveform required for the installed turnout. If your turnout is, for example, a snap switch or stall motor type, you need to add a level to pulse converter as shown in video number 78. If you are using servos, you can set the output to servo style and the pin will generate a signal to control typical servo hardware. You can then set minimum and maximum rotation angles and the speed of the movement using the profile field. See the DCCX documentation for all available values and for what pins this option is available. The last option, which is first in the list, is the C-pin option. I have added an exclamation mark as I do not recommend using it. The effect is identical with the VPin option, so a turnout position is converted to an output voltage. The reason for not recommending its use is that within DCCX it seems it is a legacy option, and there is a risk that it might disappear in future versions of the DCCX software. The other fields in the list are pretty self-explanatory, with the pin number the most important to define and some of the options only applicable for certain pin types as defined in the DCCX documentation. As always on the setup screen, click Save and Restart to make the changes permanent. This will ensure that the configuration data on the Arduino and on the IoTT stick is identical. The last topic to look at for the RedHat Shield configuration is the LED chain tab. This screen is identical to the LED chain setup screens for the blue hat and the yellow hat, so please watch video number 44 for the details of how to use it. There is one thing I would like to point out though, and that is the default settings for LED 0, so the NeoPixel installed on the RedHat Shield itself. The way the software is currently shipped, it is programmed to display the track power status. If it is off, the LED is red. When you click the side button of the IoTT stick, it turns the track power on and the LED turns green. Click the button again and the track toggles between on and idle. Idle means the track power is still on, but the locomotives are no longer refreshed and receive an emergency stop command instead. To switch the track power off, double-click the button and the LED turns red. Of course, using the LED chain setup screen, you can always change the settings for LED 0, along with all other LEDs you may connect to the LED chain. I just thought using it as power status indicator would make sense for most situations. And that's it for this video. I hope this information was useful or at least interesting for you, and you are now ready to configure your RedHat Shield once you receive it. As mentioned in the intro sequence, it should be back in the Tindie Store within the next few days, and the IoTT Stick software version 1.5.14 is already available on the GitHub page. Please do me a favor and click on the like button below to promote this video and the IoTT channel in general. Every like helps. Thanks for watching and see you in the next video.